Okay, let's talk about the statistics that we talked about right before, adding or taking the ex-ante perspective, not just ex-post perspective. When we take the ex-ante perspective, then we have to think about a bit more carefully about the concept that we just described. And also there's another dimension that you have to be careful about, which is the concept of population and sample. When we talked about summary statistics, we just said we have some data and we can calculate mean and variance and standard deviation and covariance. Then we didn't have the distinction between population and sample. But here, if you have this idea of population, then we can add many other we can add extra discussion. So continuing the example, say we have two variables again, so x and y. And the same example, x is individual heights. And y is mother's height. And perhaps we are interested in the relationship between individual's height and mother's height in general, in very general relationship. In that case, we are thinking of older people living in this planet, and also possibly we are thinking of people who lived in this planet in the past, and people who will live in this planet in the future as well. So what we are truly interested in is the relationship between x and y in very large population. So just to be exact, let's say this population here is everyone living now plus everyone living in the past plus everyone who will live in the future. So this will be the most general thing, that if you can look at everyone living now and also in the past and people who will live in the future and collect this data, their heights and their mother's heights, and look at the relationship between these two, that will tell us the most general conclusion about the relationship between x and y. So that's the population idea. The population includes every individual unit from which we can get the most general conclusion. But of course, in reality, you cannot really look at this population because it's impossible to look at everyone living now. I mean, there are too many people in the world, and it's even more difficult to collect data on everyone who lived in the past. And this is just impossible to look at everyone who will live in the future. You will get this if you live forever, but you can't get there. So population is in most applications something that you cannot really look at. This is ideally what we like to look at, but in practice it's not possible to collect data on the population, the entire population. So instead we create a sample. Example, let's say we collect data on say students taking class in Konkuk University in 2017. So this is doable. This is will not be easy, but this is something you can do if you really try hard. So let's say we collect data on every student taking class in Konkuk University in 2007 and create data set on their heights and their mother's heights. And that data set, that data is called sample. And this population that we cannot possibly collect data on is population. So when we do statistical analysis, quite often we have these two things in mind. And given the data, of course, the data we have is sample data, and we are always thinking of some population, and we are treating sample as a subset, some part of the population data. And that allows us to say more interesting thing later. So you need to understand what the difference between population and sample is when we talk about statistical analysis. Okay. So given this distinction, is this clear to people here? Okay. So given this distinction, let's go back to the summary statistics again. So I write down data again. So we have the following data, that is x1 to xn, y1 to yn. And before we just called it data, but now we will call them sample data, because now we are looking at this data as a part of what we are really interested in. And once you treat this as sample data and calculate all the summary statistics that we did, so we could calculate E of x, E of y, variance of x, variance of y, covariance of x and y. That's all we can calculate given the data, but in our mind we can think of the corresponding concept in population. So we can think of the expected value of x in population. We can think of expected value of y in population, and variance of x Now, of course, these 5 quantities we cannot really calculate because we do not observe population. We only have sample. So, but this is something really what we are interested in. If you are interested in the true general relationship between individual heights and model's heights, this will be the quantity that you are really interested in. But we don't have population. We only have a sample, one sample, and we can calculate statistics for sample, but they are not exactly the same thing as the population statistic. So to distinguish these two, usually we write some hat here to emphasize the fact that these are sample statistics, not population statistics. And also we use the term parameter to indicate that these are the quantity that we are really interested in. These are quantities that we have, so that's what we have. And that's what we are interested in. So developing this idea a bit further, this is what we are really interested in, and this is what we have. So we will interpret these quantities as indicating the true quantities. So we will call them estimates of these population parameters. So now we are adding a lot of story here. So the sample statistic, how these numbers are calculated, there is nothing new. So we can calculate these numbers given some sample, but we are adding a lot of stories here. So given this, we are imagining some population, and we are interpreting what we calculate out of sample as some estimates of the parameter in the population that we are imagining. Okay? So these are all stories, of course. We only have just one numbers for this, and we will just consider them as some estimates of the numbers that we do not know. Okay? So one last part of this story is, so we have estimates, but let's go back to this ex-ante, ex-post distinction. Ex-post, we of course have only one value here. We will have some average, some variance, and some covariance. Ex-ante, we can imagine that each of these can take different values, and also we can treat all this quantity here as random variables. So this is your decision. You may think of them as random variables as long as you are willing to talk about probabilities of each of these quantity taking a specific value. So if you are treating them as random variable in ex-ante sense, then 3 things can be distinguished. So that's here. So I'll make 2 distinctions. So E of x And we can think about the same quantities ex ante. We don't have such distinction for population parameter because obviously we don't know them anyway, so even if you wait. So there is no such distinction for population parameter, but for estimates, we can calculate the estimates after everything is determined. So that's ex post perspective, or we can think of them before we actually look at the data. And here, if we treat each of these 5 as random variable, then so there are 3 sets of similar looking quantities. Again, this is population parameter. These we call them estimates. But when we distinguish between these 2 sets, we continue to call them estimates. And when we look at them as random variable, ex ante, we call them estimator, to emphasize that this is in fact random variable.
엑스포스트 된 시점에서 이미 그거는 다 결정이 난 거 아닐까요? 그러면은 그거는 추정치 같은 게 아니라 그냥 완전 실현된 거니까 결국 인고에 있는 그 모든 거를 다 합쳤다고 볼 수 있지 않아요?
No, that's not true, because when we calculate this number, so for example, we actually calculate the covariance between individual height and mother's height from students here in Konkuk University, and say we get the covariance of, I don't know what it will be, the reasonable number, say something like 0.69. So we have one number, but we still call them estimate because we want to look at it as an estimate of the true covariance in population. So this is something we are really interested in. And what we calculate is an estimate of this number that we do not know. And when we call them estimator, then we are just thinking of what value we will have, and we are assigning probability to each possible value. Okay. So we can extend this analysis a bit further, and especially if you are comfortable by this point, then given that this is random variable, we can actually think of the mean and variance of this random variable as well. So that's the one step higher analysis. So once we consider this as random variable, it has distribution, it has probability, possible value, and probability. So for that, we can calculate again mean and the variance. Let's focus on the variance. If you think about variance of this random variable, that quantity itself, is it population parameter or the ex-ante sample quantity? So if you write down variance of E hat of x, should it be here or here? So it's not here actually. That's difficult part. This quantity doesn't belong here because it's the true variance of this random variable. And true variance should be calculated from population, not from the sample. Even if you wait, even if you look at the data, you cannot get this number because this is true variance. So this one belongs here. That's a bit conceptually difficult part. And in fact, the mean of this thing also belongs here as well. So the mean of E hat of x also should be here. So any true mean and variance, they all belong in the population. We don't observe them even if we collect data, even if we collect sample data, but this is something you cannot calculate exactly. We can only estimate this number. So you can think about, let's just focus on here. Think about estimating this number by perhaps one popular way to estimate this number is to use this number and divide this by n. That's very popular estimator. So 1 over n variance hat x. Then if you continue this idea, there will be ex-ante. This one itself is an estimator. So there you will have something that corresponds here because since ex-ante this is random variable, then this is also random variable. And if you want to continue this thing, of course, there will be multiple layers. We can again talk about mean of this quantity, which should belong here. We can think about variance of this quantity, which also belongs here. So we can think of variance of this thing, which is population parameter, and we can think of the estimate of the variance of that, which belongs here, etc. So you can just continue this forever. Okay, so the logic doesn't stop here. People don't do that, but people do talk about up to this level. Maybe not much here. So when you calculate the estimate of the variance of some population parameter, and especially if you take square root of this quantity, we have a special name for this, and that's called standard error. So in that sense, standard error is just estimates of the standard deviation of some population quantity. And instead of E hat x, we can use estimated covariance or estimated variance, other things. And all of them are called standard error. Because that's error, because that indicates the possible error in your estimate. So just to emphasize, to check whether you understand what's going on. So this thing would be called standard deviation. Of x. This one would be called standard error of the mean estimates of x. So here it will be And the numbers are of course quite different because we divide this by by n. Here we don't have n, so the magnitude will be very different. Even though we don't know the true value, we know that these two are not directly comparable number. So that's why we don't call this standard deviation, because it's rather different situation. But nonetheless, we can still interpret standard error as something like standard deviation. But for different quantity. Here, it's the standard deviation for x, and here it corresponds to standard deviation of e of x. So that's the difference. Okay, so here we have e of x here, and here we have x. So you should be able to distinguish standard error and standard deviation.
그러면은 그 포퓰레이션 측면에서만 스탠더드 디비에이션을 쓰고 그 에스티메이트를 그 구할 때는 스탠더드 디비에이션을 안 쓰는.
So the another related name, if you calculate something like standard deviation here, you will call it sample standard deviation. So we will add the term sample here to emphasize that this is not population quantity. Okay, any other question?